Once again, SpaceX is setting the stage for a groundbreaking leap in aerospace technology. But this time, it's not just about reaching Mars, it's about how we get there. Introducing the nuclear fusion Starship, a concept that for years seemed like a distant dream. But now, thanks to pulsar fusion and SpaceX's relentless drive for innovation, that dream is on the brink of becoming reality. Fusion propulsion, often dubbed as the power source that's forever 20 years away, is now taking center stage. As Musk himself supported the idea, calling it a great area of research, suggesting a future potential partnership with the pioneer of this research, pulsar fusions. What sets this fusion propulsion apart from everything we've seen before? And how does it differ from our current chemical propulsion technology? Join us as we dive deeper into the mechanics of this groundbreaking innovation. But before we delve into the marvels of fusion propulsion, it's essential to understand its foundation. Nuclear propulsion uses the massive energy from nuclear reactions to push a spacecraft forward. Instead of burning fuel like our current rockets, it heats up a propellant using nuclear energy. But this idea is nothing new. Back in the mid-20th century, scientists thought, if we can use nuclear energy to power cities, then why not spaceships? Pioneers like Stanislaw Ulam and Theodor von Karman were the first to suggest using nuclear explosions to move a spacecraft. They called it Project Orion. While it never got off the ground, it sparked interest in using nuclear energy for space travel. In the 1960s, the US started the NERVA program, and their goal was to build rockets for Mars missions using nuclear energy. These rockets would heat up hydrogen using a nuclear reactor. The hot hydrogen would then shoot out the back, pushing the rocket forward. They tested these rockets on the ground, and they worked. But due to budget cuts and a shift in focus to the space shuttle, the program was sadly stopped. The Soviet Union had a similar journey. They built a nuclear engine called the RD-0410. It passed all its tests, but like the US rockets, never flew in space. Now, you might be wondering, why go nuclear? The answer is simple. It's better than our current rockets in many ways. Today's rockets burn fuel to move forward. They work well but have limits, especially when we talk about long trips in space. Nuclear propulsion changes the game. It's more efficient, meaning rockets can go faster without needing more fuel. This could open doors to longer missions like trips to Mars or even beyond. Plus, because nuclear fuel is so powerful, rockets can carry more stuff. This is super important for missions with astronauts, where every bit of space and weight counts. And while it might sound crazy now, with nuclear propulsion, even traveling to other stars might just be possible. But before we get lost in the stars, let's dive deeper into the heart of this power and what makes nuclear propulsion so potent. And the answer lies in the very fabric of our universe. Every object, from the vastness of galaxies to the screen you're looking at, is made up of tiny atoms. Dive into these atoms, and you'll discover a nucleus bustling with protons and neutrons. Orbiting this nucleus are electrons, maintaining a delicate balance of charges. While it might seem calm and stable, this atomic structure is brimming with activity and latent energy. Picture it as a cosmic dance, a choreography of protons, neutrons, and electrons, all harmoniously contributing to the magnificent ballet of existence. Now, imagine if we could unlock the energy within this dance. That's where nuclear fission comes into play. Picture heavy atomic nuclei, like uranium or plutonium, being bombarded with neutrons. This bombardment causes them to split into smaller nuclei, releasing a tremendous amount of energy in the process. This energy, primarily in the form of heat, is what nuclear propulsion seeks to harness. It's like unlocking an atomic vault, and the treasure is the energy that can propel us to speeds and distances previously thought unattainable. But the atomic dance doesn't stop there. There's another process, fusion, which is about coming together rather than breaking apart. At extremely high temperatures and pressures, light atomic nuclei like hydrogen can fuse together to form heavier nuclei such as helium. This process, which powers our sun and all the stars in the universe, releases even more energy than fission. It's like the power of the stars right at our fingertips. So how do we translate these principles into tangible rocket designs and systems? The answer lies in the heart of a nuclear propulsion system, its reactor. Unlike the reactors we're familiar with on Earth, which are designed primarily to generate electricity, space-bound reactors are tailored to produce maximum thrust. They work by using nuclear reactions to generate heat. This heat is then transferred to a propellant, which expands and is expelled out of the rocket, creating thrust. But crafting these reactors isn't just about science, it's an art. Let's take a closer look. They must be compact enough to fit within a spacecraft, yet robust enough to handle the intense conditions of space and the heat generated by nuclear reactions. The core of the reactor contains the nuclear fuel, surrounded by control mechanisms that can adjust the rate of reaction, and thus the thrust. As we delve deeper into the intricacies of nuclear propulsion, we encounter two primary types of reactors that stand out: thermal and fast. Thermal reactors, also known as thermal spectrum reactors, utilize a moderator to slow down the neutrons produced in fission reactions. This slowing down increases the likelihood of these neutrons causing further fissions, making the reaction more efficient. It's like a conductor slowing down the tempo of an orchestra to ensure every note is played perfectly. Fast reactors, on the other hand, don't use a moderator. They operate with high energy or fast neutrons. The advantage of fast reactors is their ability to use a broader range of nuclear fuels and potentially burn nuclear waste, converting it into usable fuel. It's like playing the symphony at a faster tempo, but with the right instruments, the music is just as beautiful. But as we marvel at these reactors, it's essential to remember that the heart of any propulsion system is its fuel. And in the vast expanse of space, the choice of this fuel can make or break a mission. On Earth, our nuclear reactors often lean on enriched uranium. However, the demands of space exploration require a more diverse set of fuel options. Uranium-235 is a prime candidate, not just for its familiarity, but also its consistent fission capabilities. Plutonium-239, birthed from natural uranium, is another heavyweight, celebrated for its robust energy output. But the roster extends further. Thorium, with its unique metamorphic abilities within the reactor, and americium, a fascinating offshoot from our Earth-bound nuclear reactors, also join the list. The potency of these fuels isn't just a number, it's the very essence of propulsion. It quantifies the heat a specific fuel quantum can generate, which in turn shapes the thrust and efficiency of the entire propulsion architecture. As we delve deeper into research, we stand on the cusp of unveiling next-gen fuels that could revolutionize nuclear propulsion. Navigating the nuclear propulsion landscape, two dominant systems come to the fore: thermal propulsion and electric propulsion, each with its unique operational blueprint. Thermal propulsion, as the name suggests, capitalizes on heat. Visualize a nuclear reactor fervently producing heat, which is then directed to superheat a propellant. As this propellant heats up, it expands and is subsequently expelled with force through a nozzle, generating the essential thrust. It mirrors our conventional chemical propulsion, but with a nuclear reactor at its core instead of a chemical reaction. Electric propulsion, on the other hand, adopts an alternative approach. Here, electricity, typically derived from a nuclear reactor, is harnessed to ionize a propellant, often xenon. Post-ionization, these particles are propelled using magnetic or electric fields, resulting in a jet of ions that, upon ejection from the spacecraft, produce thrust. When it comes to efficiency, electric propulsion systems often take center stage. Their superior specific impulse allows them to achieve higher velocities using the same propellant volume. This efficiency earmarks them for long-duration missions where efficiency is paramount. However, they have a limitation. Their thrust is relatively modest, making their acceleration gradual. Conversely, thermal propulsion systems, leveraging direct nuclear heat, can attain much higher thrust levels. This means quicker acceleration, invaluable for missions necessitating rapid velocity shifts, such as entering a planet's orbit. While they surpass many chemical propulsion systems in specific impulse, they trail behind electric propulsion. Given these characteristics, it's clear that each system has its specialized domain. Electric propulsion, renowned for its efficiency, is ideal for missions where acceleration can be gradual but sustained over extended periods. Imagine deep space probes or cargo missions where time isn't pressing. Meanwhile, thermal propulsion, with its thrust superiority, is the go-to for manned missions with time constraints. Its rapid acceleration can minimize travel times, curtailing astronauts' exposure to space's intense radiation and the challenges of prolonged space sojourns. Furthermore, for missions requiring agile maneuvers, like synchronizing with an asteroid or seamlessly entering an orbit, thermal propulsion emerges as the trump card. However, with the advantages of thermal propulsion come certain challenges, and radiation is a primary concern when we talk about nuclear propulsion. The radiation emitted by the reactor can jeopardize both the spacecraft's machinery and the astronauts on board. To counter this, advanced shielding techniques are being developed. Materials such as lead, boron, and even water are being used to absorb or deflect this harmful radiation. The design of the spacecraft also plays a pivotal role. By placing the reactor at a distance from the crewed compartments, the spacecraft structure acts as an additional radiation barrier. But the challenges don't stop at radiation. The nuclear reactor, while a source of immense power, also generates extreme heat. Managing this heat is crucial to prevent potential damage or meltdowns. Advanced cooling systems are the answer. Liquid metal coolants like sodium and potassium are used to draw heat away from the reactor core. This heat is then either converted into electricity or radiated into space. In the vacuum of space, where traditional cooling methods don't work, radiative cooling becomes the primary method of heat management. Space is unpredictable, and the complex systems of nuclear propulsion can experience malfunctions. This makes contingency plans vital. In case of a reactor malfunction, automated shutdown systems are activated. Redundant systems are in place to take over critical functions, ensuring the mission continues. For crewed missions, specially designed areas within the spacecraft act as safe zones during emergencies. Monitoring systems are always active, ready to detect and alert operators to any potential issues. The possibility of a nuclear accident in space is a significant concern. Such an event could contaminate vast regions of space or even celestial bodies. To prevent this, stringent safety measures are integrated into the reactor's design. Before being activated in space, reactors are kept in a subcritical state, ensuring they don't start an uncontrolled reaction. If a major failure occurs, protocols are activated to jettison the reactor, ensuring it's moved to a safe distance from the spacecraft. But the challenges of nuclear propulsion aren't just technical. There are environmental and ethical implications to consider. A nuclear mishap in space could release radioactive materials, contaminating orbital paths and posing risks to other missions. Space debris, already a concern, could become even more problematic with the addition of nuclear reactors. Damaged spacecraft with onboard reactors could become long-term radioactive hazards. It's crucial to have strategies for the safe disposal of such spacecraft. Space exploration is not just about reaching new frontiers. It's a testament to human ambition and our relentless drive to push boundaries. As we harness the power of nuclear propulsion to accelerate our journey to distant realms, we're reminded of the immense potential it holds, yet with such power comes an undeniable responsibility. Every intricate detail, from the reactor's blueprint to the chosen path of our voyage, must be meticulously planned with safety and the environment at the forefront. As we stand on the brink of deeper space exploration, it's imperative that our approach remains both groundbreaking and eco-conscious. Act 3. Ever wondered what's powering this revolutionary leap? Let's uncover the cosmic secret behind SpaceX's groundbreaking approach. Within its infinite expanse lies a simple yet profound relationship between energy and mass, beautifully encapsulated by Einstein's iconic equation, E=mc². This isn't just a mathematical representation, it's a revelation that even the smallest speck of mass can be a powerhouse of energy. It's this very principle that governs nuclear reactions, where minuscule atomic particles undergo a transformation, releasing immense energy. This isn't just science, it's the bedrock of nuclear propulsion, propelling us into the future of space exploration. Venture with us into the atomic realm, where particles dance in a choreographed ballet, releasing monumental energy through both fission and fusion. In fission, the energy is derived from the subtle difference in mass between the original nucleus and the resulting fragments. This seemingly insignificant difference, when multiplied by the speed of light squared, results in a significant amount of energy being released. Fusion, on the other hand, is a process where light nuclei come together to form a heavier nucleus. The energy produced in fusion is calculated in a similar manner by comparing the mass of the original light nuclei with that of the resulting heavier nucleus. This difference in mass, when subjected to the E=mc² equation, releases a substantial amount of energy. Fusion reactions like those powering our Sun often release more energy than fission reactions, making them an enticing option for propulsion. Diving deeper into the realm of nuclear energy, within the intricate workings of nuclear reactors, there's a parameter known as the neutron multiplication factor, symbolized as K. This factor essentially tracks the lineage of neutrons, indicating how many new neutrons are produced from a preceding generation. When K exceeds 1, the reactor is in a supercritical state, meaning the energy production is on the rise. Conversely, when K is below 1, The reactor is in a subcritical state, with energy production on the decline. A reactor achieves a state of equilibrium, a perfect balance, when K equals 1, indicating a stable and self-sustaining chain reaction. The art of managing K is of paramount importance for ensuring reactor safety and efficiency. In propulsion reactors, striking a balance near the critical state ensures a steady thrust while preventing any potential overreactions. This delicate balance is maintained using control rods, which are designed to absorb excess neutrons, and by fine-tuning the reactor's environmental conditions. Ever heard of the Tsiolkovsky rocket equation? It's like the secret recipe in the world of rocket science, named after the visionary Konstantin Tsiolkovsky. This equation establishes a relationship between the rocket's velocity, the speed of the expelled exhaust, and the rocket's weight before and after fuel consumption. The equation emphasizes the significance of the exhaust velocity, which is a direct reflection of the efficiency of the propulsion system, especially when considering the potential of nuclear propulsion. Think of thrust as the heartbeat of rockets. It's that force that propels them, and it's all about the speed and amount of matter they expel. In the context of nuclear propulsion, the high temperatures achieved in the reactor can lead to greater exhaust velocities, translating to a more potent thrust. Impulse, which represents the total change in momentum imparted to the rocket over time, is another critical factor. A propulsion system with a higher specific impulse can achieve more significant changes in velocity using a given amount of fuel. Due to their impressive exhaust velocities, nuclear propulsion systems often boast a higher specific impulse compared to their chemical counterparts. Imagine rocket propulsion as a high-efficiency engine. It's all about converting the stored fuel energy into sheer speed and motion. Given the high energy densities of nuclear fuels, they hold the promise of achieving much higher efficiencies compared to chemical fuels. Delta V, representing the change in velocity, is a crucial metric for space missions. It determines the spacecraft's ability to alter its trajectory, which in turn affects its potential destinations and the speed at which it can reach them. With the impressive specific impulse offered by nuclear propulsion, the potential delta phi for missions can be considerably higher than with chemical propulsion. Imagine a mission to Mars that doesn't take 9 months, but just a fraction of that time. With nuclear propulsion, we're not just dreaming of faster journeys, we're making them a reality. Furthermore, the extended mission capabilities provided by nuclear propulsion mean that spacecraft can embark on longer, more ambitious missions without the constant need for refueling. This capability is particularly beneficial for missions aimed at exploring the outer planets or even venturing into interstellar space, where the vast distances involved necessitate high delta V and prolonged mission durations. In our quest to conquer the cosmos, it's not just about speed and distance. It's about ensuring every astronaut returns home safely. While nuclear propulsion offers immense power, it also poses challenges. How do we harness this force while protecting our crew from its dangers? By delving deep into dosimetry calculations, scientists have the tools to forecast the radiation levels a spacecraft might face during its journey. Such predictions take into account various aspects, from the intricacies of the reactor's design and its operational span to the protective materials chosen to shield the vessel. But how do we ensure that this shield stands robust against the relentless onslaught of radiation? The answer lies in its design and composition. The shield's efficacy is gauged by its depth and the materials incorporated. Utilizing the exponential attenuation formula, which factors in the half-thickness of materials, space engineers can pinpoint the exact thickness needed for maximum protection. It's fascinating to think that materials as diverse as lead, tungsten, and even the very water we drink can be our bulwark against the invisible threat of radiation. Yet, radiation isn't the sole challenge. The colossal heat birthed by nuclear reactions demands attention. Harnessing the age-old principles of thermodynamics, our engineers can deduce both the heat production rate and the prowess of systems designed to dissipate this heat. It's a delicate dance of ensuring the reactor stays within its operational temperature confines, a dance crucial for the reactor's lifespan and, by extension, the mission's triumph. As we stand on the cusp of a new era, our eyes set on the distant stars, we're compelled to ask, how swiftly can we traverse the cosmic distances? With the promise of nuclear propulsion, the boundaries of our exploration ambitions stretch further. Imagine, if you will, a spacecraft propelled by advanced nuclear systems. reaching velocities that are a staggering 10% of light speed. Such speeds could see us journeying to Proxima Centauri, our stellar neighbor over 4 light-years distant, in a mere 40 years. And the cherry on top, the reduced fuel constraints mean our vessels can be equipped with advanced scientific apparatus or even accommodate a larger crew. This brings the dream of interstellar voyages within our grasp. As we gaze into the vast expanse of space, the boundaries of exploration are being redefined. With SpaceX's nuclear propulsion, distant stars and galaxies aren't merely twinkling lights in the night sky. They are our next destinations. We are entering a thrilling era where science fiction merges with reality and the once deemed impossible becomes achievable. So, strap in and prepare yourself, because the future of space travel has arrived, and it's nothing short of spectacular. Stay curious, continue exploring, and always remember, the universe awaits. Until next time, keep looking up.